Hello, this is my Module 3 on the general linear model. The general linear model has two categories, or techniques. First, the multiple regression correlations, or MRC, and second, analysis of variance ANOVA. These two categories have two philosophies. First, MRC operates on the philosophy that error, or in this case residual, is present within the model, where in ANOVA, error is present within the observations. So before I delve into the data analytical side of these two techniques, I first want to talk about the similarities between these two techniques, as they do come from the same general model. First, they share similar underlying assumptions. This will definitely be elaborated on more during the data analysis portion of this presentation, so I'm not going to elaborate on them currently. Second, they offer similar hypothesis tests. ANOVA has the omnibus test, and MRC has the simple effects test. Both of these are similar, except in the extent that they analyze a different amount of variable levels. Third, both of these require linearity, and by extension are subject to additive effects. And lastly, both focus on the concept of variance. MRC uses a t-test, and ANOVA uses an f-test. T-test and f-test both can be simplified to be a ratio of variances. This ratio of variances can also be further simplified to a simple ratio of signal over noise. So first, I conducted a regression analysis. But before I could do that, I used SPSS to create a correlation matrix of our 7 predictors provided in the dataset. X1, X2, and X4 in this correlation matrix were found to be the least correlated with one another, and thus I used them for my regression because they were the least likely to have multicollinearity issues, which will be important later. So now, the results of my regression analysis. The first statistic that SPSS provided me was the Durbin-Watson statistic. This statistic displays the assumption of regression in which residuals need to be independent. So the closer that a value in a regression analysis is to 2 on the Durbin-Watson scale, the more independent the residuals are. And as a result of our analysis having a 2.045 value, we can say that this assumption is definitely supported. Next, we have the general findings of a regression analysis. We have our unstandardized coefficients, our b's, and our standardized betas. These two are the parameter estimates that allow us to get a t-score. This t-score then allows us to conduct a hypothesis test with p-values, significance values. And with this information, we have only one significant predictor of the Y3 outcome variable. And this is X1 to the level of 0.002, so it's very significant. Additionally, providing this amount of data was important within the reading of Gary King in 1980, who specified that you should provide as much data as possible in order for study replication to be as accurate as possible as well. And lastly, with this table, I wanted to talk about VIF, or variance inflation factors. This is the measure of the multicollinearity of your predictor variables, and the closer this value is to 1, the less collinearity your predictors share. And as you can see, the highest amount of VIF that we have is 1.005. So this assumption is also supported in that the predictors were not themselves correlated. Next, I ran further regression diagnostics to test more assumptions. First, the assumption in regression that residuals are normally distributed. So I used a histogram of standardized residuals, and as you can see, there's a normal curve over this histogram supporting the assumption that, in fact, we do have normally distributed residuals. Next, I used a normal PP plot to display the supported assumption that our regression analysis is homoscedastic, in that the variance is similarly distributed along the best fit line. And finally, there is an assumption within regression that outliers should not significantly or unduly influence results. And here's where we run into a little bit of problems. So as a result, I made a simple scatter plot with Cook's distance, which is the indication of how influential and how much leverage a particular point has on the B's and the standard errors of the B's in our regression analysis, and leverage, which is the extent to which an observation influences the results as a whole. And so in order to find an outlier, it's important to find points that are far away from the typical cluster of data, high on Cook's distance, and high on leverage. And as you can see in this example, in the top right of our graph, there are two data points that fulfill both, all of these requirements. As a result, these data points should be considered for deletion to make the model more accurate. However, as noted by Cortina 2002, when deciding when making outlier deletion decisions, the guidelines for this should be preset, because if they're not preset, subjectivity can come into play, in the sense that a researcher may want to keep or delete outliers to make their desired results more probable to happen. However, if you have a more objective standard and preset guidelines, this kind of subjective factor plays less of a role, and you will have less errors with replication of your study as a result. Next, I did a ANOVA of F2 and F3 with the dependent variable of F1. And I first wanted to just show the results that were given by SPSS, because there are some basic issues that influence all of them. But I just first wanted to go over what all of them are. So we have been provided with mean squares and degrees of freedom, which will allow us to have our F statistics. And if these F statistics are significant, we then are able to conduct post hoc tests. In this example, there's Tukey, LSD, and Bonferroni post hoc tests. Additionally, we're able with ANOVA to craft residual plot matrices, in which the observed, predicted, and standardized residual plots can be analyzed together to kind of see general trends. However, I wanted to address that the descriptive statistics show a key problem with this analysis of variance, in that the cells do not have a consistent n value. And with ANOVA, this is a very, very important aspect. As a result of, first of all, as a result of degrees of freedom are required for calculation of F. And if they're all varied and off, this therefore makes our F data and this general table as an uninterpretable data set, which then, because we don't have an interpretable F, we then don't have a significant F, and we then cannot conduct accurate post hoc tests, and we cannot interpret any plots as a result. Further, this inconsistency of n in this particular example highlights a violation of one of the assumptions of ANOVA. Additionally, the differences in our n violate one of the assumptions of ANOVA, which is the fact that errors need to be identically distributed, or homoscedastic, just like in regression. Before I more get into that, I also want to label the other two assumptions, as there are three, and each of them are also present in regression. The errors need to be independent. These were the residuals in regression. And lastly, in ANOVA, the distribution of errors also needs to be normally distributed. However, when we have different ends, the homogeneity of the variance is less guaranteed, in that it's easier for deviations and variance because they're all analyzed by cell, and as a result, that key violation of that assumption leads us to an uninterpretable data set. The last thing that I wanted to do with this module was quickly kind of expand my face a little bit and show that I did my handwritten work. This is my I wanted to make it so that you could look at it quickly. So I'm just going to quickly do that. And finally, for regression, we have a standardized B coefficient. And then we have our ANOVA. And finally, thank you. I wanted to thank you for watching my module, and I hope you have a great holiday.